Hi, my name's John Beans. This is a presentation that I gave to the National Association of Rocketry's annual convention in 2018 in Houston, entitled Next Generation Non-Pyrotechnic Deployment. I always think it's important when you hear a presentation from someone to understand where they come from. I have a couple of engineering degrees, and I worked for a long time at startups in Silicon Valley on everything from software to lasers to hardware and manufacturing. My kids and I used to launch model rockets on the weekends. I didn't have a lot of free time, but in 2009, I decided to slow down a little bit, start my own electronics company, and make products out of some of the things that my kids and I were playing with. My degrees are in mechanical engineering, but at Berkeley, I got into circuit design and software. And one of my real interests throughout my career has been ease of use, because I think it's really hard to design things that are easy to use. It's very easy to make things that are complicated. My family is a very nerdy household. We don't have gym memberships. We have memberships to the local tech shop where we can do laser cutting and machining and welding and things like that. And I'm the inventor of Shoot Release, and Shoot Release was a result of experiences that I had when I was getting my L1 certification. I launched my L1 rocket. The parachute ejected at apogee, of course, and it probably drifted 5 miles, which meant I was climbing barbed wire fences and crossing streams and just hoping that I could find my rocket. And you might say, well, you should have used dual deploy. It's crazy to shoot a rocket up to 2,000 or 3,000 feet on a windy day and deploy a parachute. But I've always been reluctant to use traditional dual deploy, probably because of the children that I just mentioned. And I'll talk a little bit about that, but Shoot Release was a direct result of my L1 experience. When I went to get my L2 and do practice, I built a larger rocket. It was a 4-inch diameter fiberglass rocket. It was pretty heavy, and I was worried about drag separation. One of the fascinating things to me is the things we tend to worry about. We don't always worry about the right things. And I had a pretty tight coupler on that rocket. It was a brand new rocket for my L2. But just to make sure that it didn't drag separate, I added a little electrical tape to it. Someone told me later that electrical tape is the worst kind of tape to use on a rocket because of its viscoelastic properties. But anyway, I didn't know that at the time. But I did prevent drag separation. And in fact, I didn't have any separation at all. And if you look at this chart, you can see that the rocket goes up ballistically and it comes down ballistically. I actually got that graph from my altimeter 3 from underground. That's how deeply this rocket was embedded in the side of a hill. And although I never saw that altimeter 3 again, I was able to get this download before I started digging out my rocket. So that made me think, okay, I just had this failure on deployment. There was a Shoot Release in there, but it never got a chance to be used. And I said, let's go back. Where did all this come from? Is there a better way to do this? Looking at where deployment came from, in a sense, model rocketry as we know it began with Orville Carlisle's development of a rocket that had a parachute back in 1954. A little image there of the first patent, which he got in 1956, I think, later in the 50s. And Orville Carlisle got together with the Estes family, which worked in fireworks and pyrotechnics. So that's kind of the origins of model rocketry. It comes from folks that knew about fireworks and pyrotechnics. And we still, if you look at the Rocketchute 2, Mark II there from 1956, that's pretty much what rockets look like today, with some new developments and things. But we still eject our parachutes with explosive charges. As you might say, well, what's wrong with that? It works great, right? Really lightweight, inexpensive system. Well, it gets everything dirty. Okay, I carry a towel to launches. My rocket box is just full of grit and dirt. Parachutes singed, dirty. The inside of rockets turn into little soot chutes after a while. So things get burnt. I've developed a taste for more expensive parachutes. I really appreciate good parachute construction, and it just hurts to be blowing off explosive charges onto them. And it can be dangerous. I don't know if any of you have been at a launch where you hear a pop and you see someone jump away from a table behind you. But that's probably someone, trying to test their deployment, or maybe they weren't planning to test their deployment, but that's what happened. And those tests are difficult. It's just difficult. You see videos of people in their backyards with their big rockets firing off their charges, but it's not an easy thing to test. I mean, compare that to shoot release when you do a ground test and you push a button and you hear a servo whine and your parachute falls open. That's pretty easy to test. And then there's the whole thing of timing those charges. I mean, so much of it relies on guesswork. Even if you know exactly what your rocket weighs, it depends on how windy the day is. It depends on the trajectory of your rocket. Did it go straight up? Did it go to the side? And so really timing when it comes to ejection is a proxy for what you really want. I mean, what you really want is to eject the parachute at the proper place in the trajectory, not at a certain time. That time can vary based on all kinds of factors. And deployment is the least reliable part of model rocketry. You've probably seen studies like I have that anywhere from, I think the latest one I saw was 72% of failures during launch have to do with deployment, the various aspects of deployment. And if you're a model rocketeer, you're pretty with these sources of failure. Lots of things. You pick the wrong delay timing. I do that all the time. I'll go in my rocket box. I'll want to get a certain motor. And I'll say, oh, I'll get a G78. Well, I'm all out of G78 7s. The only thing I've got here is this G78 5. Okay, I'll use that. And then of course we get an early ejection you've got a rocket that's a little bit messed up at that point. That can cause zippering. Even if you're using electronics to time your ejection, maybe you didn't set it up right. Maybe you had a wire loose. Maybe you didn't turn it on. I've seen folks at launches toast their electronics, go buy a brand new one from the on-site vendor, hook it up and fly it. And I guess they just hope that the default settings are correct because, it takes a long time to set these things up, and sometimes people just kind of go with it to start with. Igniter failures that chuff if you're relying on a secondary charge to eject a parachute and the igniter fails. The ejection charge chuffs or falls out along the way, gets starved of oxygen and way up high, or you didn't put enough charge, and that's frequently why people double whatever amount people tell them. They think, well, if a little bit's good, let's make sure we get enough charge here. Or mechanical interference or failure. That's what happened to me on my L2 attempt. I just frankly couldn't separate the two halves of the rocket. Sometimes you'll even have a charge go off and the chute will still be stuck in the tube. There's a thing I like to call the Big Daddy effect, where you've got a nose cone that can vent without coming completely off. Sometimes that's all you get. You get an ejection charge, a nose cone that hasn't come completely off. So there's all kinds of things that can happen. And even if you're using something like shoot release, you can get it ripped away at ejection. Maybe you tether it to the shock cord in a way that when the nose cone flies off and the shock cord pulls tight, it also pulls shoot release off of your parachute. All kind of things that can happen here. I wouldn't have believed this if I hadn't seen it, but at one of our launches, I saw a rocket flutter to the ground using shoot release, and it was because the Nomex blanket was just loosely wrapped around the outside of it, and for some reason in the slipstream, that the blanket never got whisked away. It just, even with the shoot release already released, the whole parachute kind of stayed in a bundle because the Nomex blanket was kind of wrapped around it and perfectly happy to stay there all the way down to the ground. So there's all kinds of things that can go wrong with deployment. I mean, we know that deployment is far from perfect now. So that kind of began my thinking, how do we improve upon the pyrotechnic deployment method created back in 1954? Feels like we could use a little more progress. I mean, here's how I would describe, kind of chart our progress in the hobby. We started with, Rocket 1.0, 1954, one explosion, the parachute pops out. Then we said, oh, well, that parachute, this is like my L1, right? The parachute coming out at the top, that's a long walk on a windy day, and maybe our field's not that large. Let's go to dual deployment. So we went to 2 explosions. One up high with maybe a drogue chute, one down low with our main. Well, then shoot release came along a year or 2 ago, and that kind of got rid of that second explosion. And it basically said if you can get your chute bundle out of your rocket We can use electronics to decide exactly when we want the second chute to open. Just like we did with dual deployment, but this time there's not an explosion involved. Here's what I think we need to get to, and that's Rocket 2.0, and that's no explosions at all. That's get the chute out at apogee with electronics and decide when to deploy our main also with electronics. And then we would only use our engines, our rocket motors, for the up part, for the lift part. And everything after that would be handled by electronics. And so, you look, how are other people doing this? If you look at commercial rocket flight, if you look at the United Launch Alliance, and what they're doing with Titan, there's a 3-part fairing that they open up to deploy satellites. You look at SpaceX, there's a 2-part fairing that they use. So there's inspirations here for the way that other people are doing deployments that aren't pyrotechnic. And actually, the interesting thing when you start to look at these, if you look at the Falcon 9 user's guide from SpaceX, you'll see that they talk about one of the features of their fairing being that it relies on non-explosive pneumatic release and separation systems. Well, there's good reasons for that, right? You don't want to be throwing stuff into space, into orbit. There's already enough junk up there. They like the fact that you can test it. And in other words, if you've got an explosive pyrotechnic bolt, you run a test, right? You go pow, and that bolt goes off, and you say, okay, that bolt worked. But then what are you going to do? You're going to have to take another bolt and install it before flight. So you're not really testing what you're using. You're testing something like what you're using, and you're testing other parts of your setup, but you can't completely test it because it's destructive. And then I found this really most interesting to me is here's even SpaceX saying that they want to eliminate hazardous pyrotechnic devices. Come on, if SpaceX is thinking about safety and explosions, I think we can too with our. So here's the goal, okay? If you're gonna evolve this, if you're gonna change this and make it better, you've got to do it right. It's got to be reliable, complete release. A deployment that only half happens isn't deployment. Testable. We just talked about testable. Anything we come up with that lets us convince ourselves before the launch that it's going to work is a good thing. Redundancy. I'll even go out on a limb on redundancy and say that redundancy is always good. I mean, you have to have redundancy for an L3 certification, but I would even say redundancy would be good if you were launching with Boy Scouts in a schoolyard. Redundancy is always a good thing if you can afford it, if there's room for it, if it doesn't cost too much, it's a good thing. And then whatever solution we come up with, you guys know everybody likes to fly different kinds of rockets. They want a rocket shaped like they want a shape. Some guys are into the alpha. Some people love scale rocketry. They want it to look exactly like a Saturn V or a Mercury. You can't come up with a solution that makes the rocket suddenly weak or way too heavy to actually work. Okay, so those are things we need to think about when we design a solution. Give us the freedom to make a rocket like we want to make it. Make sure that it's strong enough. We don't want to be worried that we're coming up with something that's rickety. Don't make it too heavy. I mean, there's people that want to set altitude records, and you don't want to have things that compromise that. We want to be safe. That goes without saying. Easy is always good. Reusable, much better than things you need to replace or refill or throw away. And cost effective. Cost always matters. We'll take all these things we want to do above here in terms of goals, and we want to be able to make them as affordable as possible. Here's the thing I was thinking about. When you're trying to solve this problem, it's interesting to think about the relative deployment energy that's required to get the job done. Okay, and if you look at a current solution, let's say you take a 9-volt battery, and you don't have to use a 9-volt. That's very common. That's probably the most common battery people put in their secondary deployment systems. That battery weighs about 45 grams. It's got 8,000 joules, roughly, give or take, of energy in it. And you're going to use that to set off a black powder charge. And even 1 gram of black powder has 3,000 joules in it. And I'm kind of glossing over the fact that there's an igniter there in the middle that also has some energy. But here we are taking 11,000 joules of energy to deploy a chute, to eject a chute. Okay, now we're going to transfer 1 joule of energy from that battery to ignite the igniter, which will ignite the black powder. And that will give us that 3,000 joules of energy. So we have this whole system set up here to cause 3,000 joules of energy to be deployed. Okay, so that's kind of it's kind of a way to think about this if you're thinking about deployment energy. Let's contrast that for a second with shoot release. Shoot release uses a tiny lithium-ion battery. It weighs about a tenth of what a 9-volt weighs. Now you could say, okay, you could use that for the other solution too, but I'm just, and that's true. You could reduce the weight of the first solution, but this is exactly what shoot release uses. It uses a 3-gram battery. It transfers the same rough energy, 1 joule, to a servo, and this servo weighs a little under 2 grams. And that servo lets your chute go with about 1/4 of a joule of energy, and that's being generous. So let's compare this for a second. Let's say this is the secondary event of a rocket flight. We use 3,000 joules to explode a parachute out in one case. In the other case, we're going to use 1/4 of a joule to let go and let a parachute open. So this isn't the only way you have to do it. Lots of other ways to do it. There's all kind of savings and things you guys can come up with for this, but I'm just telling you, this is kind of what's going on in terms of relative deployment energy on a secondary event. So it's just interesting, like how much energy does it really take to get the job done? Go back to first principles and say, one virtue might be come up with solutions which require very little activation energy at the time, okay? Just that's kind of how I think about these things, and maybe it'll spark some thoughts with you too. Okay, so we looked at the SpaceX United Launch Alliance approaches to fairing. That's one way to do it. A fairing is the name of anything that's got a streamlined aspect. But you could also do it in a payload section, and that's a little bit more like what we're used to when we do dual deployment. We'll have a payload section. Here I'm proposing that we make a payload section that opens. And so let's compare these two. Which approach should we do? Should we just make a new kind of electronic fairing that goes on the top of a rocket? Should we make electronic payload sections? How should we do this? Here's the challenges. No matter which way we pick, we need to make it strong during boost. We can't have it flying apart if we have a high thrust motor. But even though it's strong on the way up, it's got to fall apart at deployment, right? And then we have to figure out the electrical and the software parts to kind of make that happen. So think about that. On the one hand, you want it to be incredibly strong on the way up, and then all of a sudden you want it to just fall apart. So here's the relative merits of those two approaches. If we go with a nose cone fairing, it is somewhat mechanically simpler if you work through it. I'm not saying it's obvious just by looking at it, but I'm just saying, having looked through it a little bit myself, I think it's somewhat mechanically simpler, but it is expensive to make supersonic. It's expensive to make something like that opens, but that can cope with the heat, especially of transonic flight. But here's the killer on this one. There's many variations needed. In other words, as soon as you pick a shape for that nose cone, that nose fairing, you for instance, can't make a Nike Smoke, which has the sharp nose cone. You can't make scale stuff unless it just happens to have the exact same nose cone as that. But if we move to a payload section, it does get a little more mechanically complicated. It's suddenly got two interfaces, the top and the bottom, that connect to things like the nose cone and the fuselage. Those tethered parts could tangle, but it is more universal. Almost every rocket design, even the scale ones, have a circular cross-section part of them. In other words, you can always find a place in a rocket where a cylinder can be put. Still make the rocket look like you want to look like it. Not all of them, but the vast majority of them. For instance, here's that same payload section on a Nike Smoke, for example. So you can see that we couldn't have done that with the nose fairing approach. We can do it with a payload section approach. Let's talk a little bit more about those mechanical challenges, because it does need to stay together on the way up, but it must reliably and completely fall apart and use low energy to do so. Remember, that's one of our virtues here, is low activation energy. It should be cheaply constructed. And when you think about all those constraints, it becomes an interesting puzzle. You're trying to make something that is reliably rugged, but has a little fatal flaw you can activate that makes the whole thing fall apart. Let me walk you through a construction of what something like this might look like. And this is just one way to do it, not the only way to do it. And that is to have cheap injection molded adapters. You attach couplers to your standard parts, including making ones that are vented so that if you still have engines with ejection charges, they won't interfere with anything. We're just going to throw the ejection charge away. We don't need it. Any redundancy that we need, we'll do electronically. And after a while, we won't even have engines that have ejection charges anymore. The bottom part of the rocket's the booster. It is only there for the up part. It does not need to have an ejection channel. We'll vent it if we still got engines that use ejection charges. If we have a choice, we won't even put the ejection charge in the motor. And then what we'll have are payload bay doors and smart couplers. And the electronics will be in the smart couplers. The payload bay doors will be very inexpensive, probably injection molded, rugged plastic. And notice here, we've got two couplers. We'll design this in a clever enough way that if either one of those couplers releases the payloads, they'll both fall apart. So we can make it redundant by putting electronics in both couplers, or we can just put them in one end if we're not as concerned with redundancy. Here's an actual example. I've done some analysis. At the presentation at NARCON, I passed around a 3D printed model of this. And one of the things that helps us during rocket flight is that most of the stress is caused by compressive forces in a rocket. There are some lateral forces and moments and shears, but it's mostly compressive. There's relatively little tension in a rocket. You do get some of those when you've got corkscrewing because you've got some thrashing around the rocket and some moments that are introduced. Usually those won't rise to tension because there's so much compressive force being put on them, but you do get variation because of that non-optimal flight. But this part, this coping with compressive strength is relatively straightforward to design. There are some great engineering plastics now that are in some cases as strong as steel. And the difference in price between a very cheap plastic and a very expensive plastic is on the order of dollars. And so we've got some amazing materials that we can work with today if we need them. But like I said, this is not that overwhelming of a mechanical design problem. Here's what a rocket looks like during boost. Notice we've actually got a vented coupler there just because to exhaust the ejection charge from the motor. You might not need that later if you have motors that are plugged and don't have ejection charges. And what happens is it falls apart. When the couplers release, the rocket falls apart. In this case, you've got a parachute there that's bundled up. You can put a chute release on that and have a dual deployment system there. After you release, what affects reliability? Well, this is trickier than the boost phase, okay? Because it's got to just disintegrate with little activation energy. And it shouldn't hang up or jam or tangle. That's going to be our challenge here, I think. But with clever mechanical design, you can reduce the cost and increase the reliability and take some of the burden off of the electronics. In other words, you can imagine very complicated electronics with sliding guide rails and lots of hooks and things like that. Or you can come up with a mechanical design that has a little fatal flaw that the electronics can trigger. Kind of tough for me to explain that without showing you one, but that's the goal here. So we need cheap tube adapters that we can add onto existing rockets, cheap payload sections or fairings. If we do the nose approach, that's called a fairing, but cheap plastic doors. If we break one, it's a few dollars to replace. Couplers, both smart and dumb. Remember, if we design a coupler correctly, if either end of the payload bay doors releases, the whole thing falls apart. If we make them both release, we've got redundancy. It's going to fall apart no matter what. And then portable little smart actuators. I think if we do this correctly, we'll take all the brains and the actuator part of this, make it modular, so that what you're essentially doing is you're equipping your rockets for electronic deployment by putting cheap adapters in your fuselages and on your nose cones. You can swap the sections across rockets, but you can also swap the guts, so the electronics parts. You don't need as many sets of those, and you can snap them in any rocket, whether it's a a 2.6 diameter inch rocket or a 5.5 inch diameter rocket. You'll use the same electronics for both. That's a virtue, that modularity. And once we've got this kind of payload thing, we can use it with shoot release for dual deploy. So we'll pop open our fairing at apogee and we'll have our chute wrapped with shoot release, or a drogue and shoot release, or a drogue and shoot release on a bag, or drogue and shoot release with a mechanism. So that bag and that mechanism are things we're working on now that would let a standard shoot release deploy, for instance, a 10-foot parachute by a clever mechanism that holds a bag closed, for instance. Remember, it doesn't matter how big the parachute is. It can be a 12-foot diameter parachute. It takes very little activation energy to trigger a latch to let a drogue pull a parachute out of a bag. Keep thinking about activation energy. I've found that to be a useful construct for me. So if you look at the top things we need to develop, we're looking at injection molding economics, the cheap tube adapters, the cheap payload sections, the couplers. These are parts which don't cost much in volume. There are molds that need to be bought, but we're kind of used to doing that. So that's something I'm comfortable doing. But that lowers the cost of the overall solution. And then, if we have portable smart actuators, and you can kind of use shoot release as an example of this. You don't install shoot release on a rocket. You can carry it around and use it on all your rockets. You can loan it to a friend, right? But I think we need to do our payload bay doors this way too, and make the actuators on those modular and transportable, so that we're not installing them in a rocket. We're just moving them from rocket to rocket, and we can loan them to a friend if a friend's breaks or something like that. So let's talk about some of the implications of going with a system like that. It'll make dual deployment more widely available. I think everybody ought to do dual deployment. I think Cub Scouts in the schoolyard ought to do dual deployment. Safe, no explosives, no mess. I'm really looking forward to this. More modular reuse across your fleet if we do it right, like shoot release. I mean, think about when shoot release came out. I don't think everybody really fully appreciated the value of something that was easy to move from rocket to rocket versus, for instance, a dual deployment altimeter, which you would screw into a payload section, install in a rocket, run wires, connect wires, hardwire everything up. Suddenly you've got something that not only moves from rocket to rocket, doesn't get installed, but actually sets up a lot quicker too, right? Than a dual deployment altimeter and a charge and wires and all of those kinds of things. So modularity is a good thing. We ought to try to keep that going on this. No timing, no delays. There's no such thing as timing anymore, right? Timing was a proxy for when to deploy a parachute anyway. Now what we'll do is we'll have payload bay doors that always open at apogee, and we can run whatever engine we want. I mean, grab a G80, grab an I-210. It doesn't matter. What is the timing? There's no timing anymore. You're just choosing how much impulse you're going to lift your rocket with. Deployment is a separate thing. We're not loading that onto the rocket engine anymore. We're doing that with electronics. And it's simple. If we do it right, just turn it on. Make sure that it's on and it'll work. And it's very testable. You can stand your rocket up on the pad, trigger a test mode like you do with shoot release, and the thing should fall apart. You can test that as many times as you want. Some further implications. Well, there's no zip ring anymore. It's kind of eliminated structurally because you've got these plastic couplers that you're putting on the end of every fuselage. So that's where your eye bolt is. You've no longer got a mounting point down in the tube of your rocket that can get zippered. We don't need things that have to do with ejection charges like baffles, blankets, dog barf, wadding. We don't need to worry about engine variations anymore when it comes to delays. You just pick your impulse. You pick the diameter of your motor, your impulse, make sure the length fits, and that's it. You're not looking for an F87.7 versus an F87.11. You're just putting the motor in. No heat and corrosive residue on our shock cords, our electronics, our parachutes. No explosive pressure in the fuselage anymore. You're not blowing up a bomb inside your fuselage. I don't even know what that means necessarily for how we design fuselages. It means if we want to, they can be vented. They don't need to be airtight. I don't know what that means for what the rear closure, for instance, looks like. What we can do to eliminate base drag using vents and things like that. There's all kind of interesting things that people can think about to do there. It just means that one of the casual assumptions about fuselages that they are charge tight or that they then need to be vented for high altitude flight, blah, 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 don't matter anymore. In fact, I would say that given that you might put altimeters in various places of your rocket, vent everything. And here's another implication. L3 is suddenly not a different design. For instance, if someone at a schoolyard is doing dual electronic deployment, they're already kind of building an L3 rocket. The difference is L3s have a lot more impulse. They're a lot more dangerous. They're made of different materials. They go to much higher altitudes. But logically, they're not a different design. If you get good at electronic dual deployment, non-pyrotechnic dual deployment on a small rocket, on a rocket the size of an Estes Pro Series 2, then when it comes time to do your L3, you know all the elements of that. And along with all the written knowledge that you need and the tests you need to do and the documenting of your build, you've kind of already got a redundant rocket. Some final thoughts. Weight will be a challenge on this. The original method of pyrotechnic deployment developed by Orville Carlisle in 1954 may never be surpassed in terms of how little it weighs and how little it costs. Very clever. You just burn through to a little ejection charge, and the energy from that ejection charge will blow the chute out. So when it comes to weight and cost, really nice optimal solution. It's just all those other things, all those other limitations that are what leads us to this presentation today. I think that with careful mechanical design and material selection, you can get this to a very low activation energy, very reliable system. And I think the materials that we can use for this can be cheap and can have fantastic properties. And I still think, even with this, you may say to yourself, well, oh God, everything's getting so automated and plasticky. You've taken all the fun out of balsa and cardboard tube design and construction of rockets. I don't think so. I think now you could put loving attention into, for instance, a Mercury scale model and feel a lot more confident that this thing's going to get back to you, right? You're going to have advanced electronics inside your rocket. You're going to have nice, clean deployments. You're not going to have any explosions going off inside your Mercury scale rocket that you put so much time and attention to. I think there will still be room for craftsmanship. But I will say that until we get really, really good at lowering the weight and cost of this approach, I'll grant that you probably won't see these being used for record altitude attempts or for people that are really, really budget limited. But I think probably in the long run, this is probably only limited by the cost of materials. I think this will be very, very inexpensive not too long from now. That's all I had to say about this presentation. Love to hear your feedback. Send me an email at john@jollylogic, and happy flying.